Welcome to Topcast. And today, for a special presentation, I was fortunate to attend a lecture recently by Professor Julian Barbour, who is an independent British physicist and one of the foremost experts on time, Newtonian Mechanics, and, well, the foundations of physics in general. He's a very original thinker who is speaking about a new theory of physics, shape dynamics. This is a technical presentation, which is unusual for Topcast, and you'll hear there are frequent interjections and questions from the audience from a number of other experts, physicists like Charlie Lineweaver, who has appeared on Topcast, and friend of the show, Sam Kuipers, and others. The audience questions and interjections are audible and in most cases intelligible, enough at least, but the audience obviously weren't all mic'd up, so they're more difficult to hear. However, Julian is being properly recorded so you can hear his answers. Now, after my disembodied voice here, you will hear an introduction from our disembodied Sam Kuipers, welcoming Julian to the stage, and then a disembodied Julian speaks for about a minute before we move on to the embodied video of Julian delivering his lecture. This is a wide-ranging original talk, and you can watch for the content, and you can watch for the deep knowledge Julian has of the ideas and the history of physics, and how Newton might still have a chance at being more right than what anyone else much thinks. And also for the interactions between physicists in the audience questioning one another and Julian in an attempt to understand something that challenges the foundations of our most basic ideas about space and time and reality. So without any more from me, here's Sam. And then Julian.
Yeah, well, Julian, thanks so much for being here. It's great you could join. Julian is really an expert on time. He's one of the experts on the theory of time. I first encountered Julian's work a couple of years ago. I work on time myself, and I was very pleasantly surprised to find Julian's work, which was really mind-blowing to me. His books are absolutely excellent. I cannot recommend them highly enough. I think Julian is interesting both in that he's an advocate of the timeless view of physics, in which time is really reduced to other, more fundamental attributes, and also because he's an immense expert on classical mechanics, on the ins and outs of Newtonian dynamics. And when I first encountered Julian's work, one of the things that really struck me was that I thought I understood Newtonian mechanics, because of course I had high school classes and things like that in physics. And then I found that really I was very deeply mistaken about this. So that's one of the things that makes Julian's work really fascinating. And I'm very honoured that you can give a talk. Please give a warm round of applause for Julian.
All right, thank you very much. Well, thank you. And at the bottom you see many thanks to Naval, Brett and Sam. I thought, Sam, you'd suggested I should be one of the speakers, but Brett tells me he'd already decided on that. But anyway, thank you very much. So you see my title is Shapes, which is going to be very important, Time and Holism. I'm going to suggest that we need a paradigm shift from reductionist approach to physics and science to a holistic one where we really try and understand the whole universe. So here's me, vanity, showing my own picture. This is really to illustrate the triangles. People who've heard me talk before know I'm always illustrating my points with triangles, because a triangle is the simplest non-trivial structure, a shape. And the point I really want to emphasize again and again is a triangle has a shape and a size. And the shape is far, far more fundamental. The size only has meaning if you've got a ruler to measure the size. And if you look at that picture there, you see the triangles are smaller than me, and I'm smaller than the room in which I was speaking, and the room was smaller than the rest of the universe. And you'll go on forever looking for something to measure the size, but it's always relative. So use nothing but ratios. I'm going to have that carved on my gravestone. I just say this, I recently had a visit from a wonderful French mathematician who came with his student, a Chinese lady, and I got her to write out in Chinese characters how they represent complexity. There's one with 3 symbols and one with just 1 symbol, and also entropy. And first of all, it was absolutely magical to see her doing this, and the ease with which she did it. But then the point I'd like to make is that the meaning of those symbols is completely independent of the size. If she'd written them twice as large, they'd still have exactly the same meaning. And I'm coming to think that meaning is scale invariant. And also I would say my talk will really be about three-dimensional scale invariance, and I would assert that it's an understudied symmetry. It's been neglected. So this is about holism, so that meaning is encoded in a whole. There was a book came out in which there's a chapter from me, It from Bit, that's John Wheeler's aphorism, and I argue that it's bit from it. Without having the whole story, you can't identify a bit. You've got to have the whole structure there. And the German word for shape is Gestalt. And in Gestalt psychology, that's an organized whole perceived as more than the sum of its parts. And the attributes of the whole are not deducible from the parts in isolation. And I think I'll be able to illustrate that in Newtonian gravity. Now, I got into all of this quite by chance reading a Popular Science article about work that Dirac had done in 1958, which was reflected in a book which he published, a very little book, Lectures on Quantum Mechanics, which is very important in gauge theory and is a very much cited little book in papers on gauge theory. And in that, so what Dirac did, instead of looking at general relativity as a space-time theory, he'd looked at it as a dynamical Hamiltonian theory. And he'd come to the conclusion that arbitrary slicing of space-time to define simultaneity was just introducing unnecessary complications and redundant degrees of freedom. And that was, from the point of view of a quantum theory of gravity, was anathema to him. So he has this statement, which he puts in italic: I am inclined to believe four-dimensional symmetry is not a fundamental property of the physical world. I read that one evening, and the next morning I woke up and said to myself, well, if Dirac says that, what is time? And that was 61 years ago, and I'm still working on that problem. So that's the background to me.
Four-dimensional symmetry.
Sorry?
What is four-dimensional symmetry here? What does he mean by that?
The notion of space-time, starting with Minkowski space-time, which has a four-dimensional. But the thing is that you can, in general relativity, you can foliate. You can get Cauchy surfaces which slice four-dimensional space-time in any way you like, as long as it remains space-like. And he said that that's a mistake. You should restore. And in fact, actually, when you go into the structure of general relativity, the most economic way that uses the least information is to replace the idea of space-time just by a succession of shapes, of three-dimensional shapes. I've been involved in that work, and it is closely related to a very fundamental property in general relativity, how you solve its initial value problem. So then, very soon after that, I came across works of Ernst Mach, where he says it is utterly impossible to measure the changes of things by time. Quite the contrary, time is an abstraction at which we arrive by means of the changes of things. Now, that's realized in what's called ephemeris time by the astronomers. So in the 1890s, the astronomers detected an anomalous acceleration of the moon. The moon was further ahead in its position on the sky than it should be, according to Newton's laws and the assumption that the rotation of the Earth is a good clock. So they then, and there was a rival theory that at eclipses of the moon, the sun's gravitational force was absorbed by the Earth, so the moon didn't feel such a strong gravitational force. That was only disproved in 1937 when it was shown, when a British astronomer showed that all the planets exhibited this thing. So it couldn't be anything to do with the Earth absorbing the things. But what the astronomers decided was that instead of using Newtonian theory with Newton's absolute time to predict where the planets would be, they assumed that there would be something like Newtonian time, above all one which would conserve the total energy of the solar system, and they would use the position of the moon. Essentially, they were just using the sun, earth, and moon. They would use the position of the moon to say what is the time, and that they called ephemeris time. And it involves all the elements in the system, and this is why I have some discussion with Sam about this idea of Page-Wooter, where you take 1 degree of freedom as to tell the time for the rest of the ones. I think they are all, I would argue that they're all involved together. So much for that for the moment. Now, Mach's conjecture otherwise was the origin of inertial frames of reference, which is the modern way of talking about absolute space and time. And when, I don't know, people here might reflect on this, most students, when they're taught dynamics in their first year at the university, they're told Newton's laws in an inertial frame of reference. If any of them is so cheeky as to ask the lecturer, what's an inertial frame of reference and where does it come from, they'll probably be told it's one in which Newton's laws hold. That's not an explanation. Mach's conjecture was that the relative positions and motions of all the bodies in the universe determine the local inertial frames of reference in which Newton's laws of motion hold. That's come, in that form it's also called Mach's principle, but I don't want to get into Einstein's coining of Mach's principle, and I have to say Einstein made a terrible mess of trying to sort out Mach's principle. He did other things absolutely wonderfully, but not that. And this is realized, I'll show how it's realized in Newtonian gravity, but it is also realized in general relativity through elliptical equations that hold instantaneously on a space-like slice. And it's in the ones that don't contain time, G0 I, G0, G01, G02, G03. And that's, if you're interested, so this is in a book by my collaborator Flavio Mercati, Shape Dynamics, where all of that, if any of you want to look at that, it's published by Oxford University Press a few years ago. Now, I want to introduce the notion of intrinsic shape dynamics. So Newton introduced the notions of absolute time, space, and implicitly with absolute space, a notion of absolute scale. And I would say that's the most pernicious aspect of it all. So let's suppose we have particles with masses mi, 1 to n, and they're at Cartesian coordinates ri. Now they will have these observable separations rij that you see in the middle there, at the top, but that presupposes an extrinsic absolute scale to say what those separations are. You can't do that without a ruler. And that, I think, is just amazingly often forgotten. Now, you can rectify that problem by making things dimensionless. So there is an extrinsic scale in Newtonian theory, and it's the root mean square length. And if the particles all have equal mass, it's the one on the left, up there. And if you add the masses, mass weighting, where capital M is the total mass, that makes it, that's something pure, it's a pure number, it's dimensionless. And then you can, you introduce then what I call the intrinsic separations. Those are pure numbers. And everything should be pure and should be ratios. And you can do this even if there's infinitely many particles in an infinite space. And we're working on that. It would be too complicated for me to go into that. So now I'm a bit influenced here by Poincaré's writing on this. Poincaré says we should take Newton's second law, but he too was very doubtful about absolute space and times like that. So the question is, keeping the essence of Newton's second law, which is the relationship how forces change motions, can we seek a Newtonian evolution of these intrinsic separations, not the absolute ones? And the answer is we can, but the key thing is, let me start off. So I'm going to start by defining what I call undeniable difference. Suppose we have one shape, Rij, and then there's another shape which is slightly different. So I add a little bit more of those things. And these are the R bars, the intrinsic. These are the intrinsic separations. And there's no criterion for a time order in that. So the question is, and this is derived from Poincaré, but I go at least one or two steps further than Poincaré. Can two such shapes define an evolution of the shapes from then on? Uniquely, is that. Then you would say that's a wonderfully predictive theory if it can do that. Now, Newton's theory as it stands can't do that, because the way I put it is he contaminated his own greatest discovery, which was the second law and the gravitational law, because first of all, absolute time allows you to assume different amounts of infinitesimal time pass between those two intrinsic shapes. So, and that means that you can imagine an arbitrary amount of kinetic energy being associated with those two shapes. So there's an arbitrary element coming into Newton through his absolute time. There are various ways to get rid of that problem. The most obvious one is to say, well, there's only one value of the energy which is distinguished, which is that the energy is exactly zero. And you can argue for that by what's called the principle of sufficient reason. But there's another reason, another argument, is that you can get rid of time altogether. And you just say that there are successions of shapes, and you have a shape space. This is with scale, by the way. You have a shape space, a space of possible configurations, and you define a geodesic principle in that space, which is not involving time at all. And then you can define, so that's the simplest possible law you can get. It's a geodesic law, and you then imagine that evolution unfolds at a certain rate, which makes Newton's laws hold and energy conserved. And that's a convention. But in fact, all the reality is in the successive configurations. It's not in the rate at which they follow each other. So that's there. So that's the first thing. So that's the contamination with, we get rid of the contamination due to absolute time by saying the energy of the whole universe that I'm consisting of, a finite number of particles, must be exactly zero. Now the same thing is you can introduce arbitrary orientation between the two. Here's my one shape and here's my other one that's slightly different. I can imagine this is oriented in absolute space relative to that. It won't change either of the shapes, that thing there, but I'm putting actually effectively angular momentum into the initial data when I do that. So that's streng verboten, as the Germans would say. You mustn't do that sort of thing. So the only way to get around that, well, people who know my work on best matching says the angular momentum must be zero. And that again would follow from the principle of sufficient reason. Only vanishing angular momentum is distinguished.
Julian, I have a problem. What is the principle of sufficient reason? I don't know what that is.
Well, Leibniz said any definite observable fact, Simon can perhaps put it sharper more than me, must have an explanation.
Any observable fact must have an explanation. Would you agree, Simon? Yeah, something along those lines. Yeah. And it's the supreme confidence of the rationalist. And if you think Leibniz was a bit over the top, Gödel said Leibniz was by far the best
thinker on this, far superior to Spinoza, according to Gödel. So I think there's good reason to take that seriously. It's the supreme rationalist standpoint that there must be an explanation for something you can see.
Sorry, without wanting to open too much of a can of worms, what counts as an explanation there? Is that causal theory?
Not necessarily. In fact, I will give you examples where there's an explanation for a structure which is not due to something that's happened in the past, that it's just an instantaneous explanation.
Is Voltaire's Candide, does it make fun of this principle?
Beg your pardon?
Does Voltaire's Candide make fun of this principle?
Oh, absolutely, yes. Well, no, Leibniz said the universe should be, he believed that variety, without variety we could say nothing. Therefore, in the best of all possible worlds, there should be more variety than anything else. And then when he was talking to princesses, he said, this is the best of all possible worlds. But really he was saying it's the most varied. But a better characterization of his philosophy, which I'll come to, is that the universe is striving to become ever more varied. And I'll show you exactly how that comes straight out of Newtonian theory when you've got rid of all his contamination of his own wonderful theory. Now we come to scale, and this is where things get, for me, extremely interesting, and is a very recent development in the work I've been doing with collaborators. Now, you can also put an arbitrary scale difference between these two shapes, and say one is larger than the other. And that would be measured by something which is analog of the angular momentum, but instead of a cross product, it's a dot product. So that's what I call the dilatation momentum. Now, here's an interesting thing. That quantity d plays a very fundamental role in celestial mechanics and among n-body specialists. Amazingly, I was the first person to give it a name in 2003 and call it the dilatational momentum. So that's quite an interesting fact of these things. And just as there was some talk of the Riemann hypothesis, who knows about Michael Berry's work on the Riemann hypothesis? Michael Berry has found a way of finding a quantum mechanical Hamiltonian which whose eigenvalues are very close, reproduces a lot of the zeros. And I was talking about this in Bristol, this stuff, showing my dilatational momentum, and Michael came up and said, by the way, my work is based on that. It's just the dilatational momentum of a single particle in a plane. So that's quite an interesting fact. Now, there's all sorts of problems with saying that I want to have the dilatational momentum zero eternally. First of all, it's not conserved by the Newtonian force. The Newtonian gravitational potential is homogeneous of degree -1, and you need one of degree -2 to ensure conservation of that condition. So there are other problems, but let me point out that I explored that possibility just over 20 years ago, but then abandoned it because it just wasn't working.
So can I ask just a quick question? I might have missed this, but everything is referenced to the center of mass of the system.
Oh, yes, center of mass, yes. So this best matching idea of mine brings the centers of mass to coincidence and the angular momentum to zero. Right. Yeah, and if you want to, you can bring the dilatational momentum to zero as well. But then we might have time to talk about that later. So where do we go from here? And this has come really in the last year or two. So the solutions with energy and angular momentum exactly zero, these are solutions that in normal Newtonian terms are a set of measure zero. So now the question is there an even smaller set of measure zero within the set of measure zero, which actually gets rid of this problem of absolute scale?
Julian, when you say it's a set of measure zero, what is the set within which it is a set of measure zero?
All the ones that start with arbitrary initial data as specified when n-body people write down the equations, so they can have arbitrary energy, arbitrary angular momentum, arbitrary momentum, but that's trivial. So basically you're instead of allowing initial data which have energy and angular momentum non-vanishing, you're saying only the ones that have vanishing things. So that's the set of measure zero, I think you would agree. Okay. So now the question is there just possibly a set of measure zero within that already tiny subset? And the answer is yes, there is. And that goes back to what most people regard as the most fundamental principle in dynamics, the principle of least action. Now, I'm suggesting that the principle of least action is too restrictive, because in the principle of least action, you require to specify an initial configuration. Normally there's a length of time, but it doesn't have, in a geodesic principle, it doesn't have to be a length of time. But then there has to be another configuration, and those two configurations will have different scales. There will be a ratio of scales. And to say there's a ratio of scales, you've got to have a ruler at one end and a ruler at the other end. But that's introducing absolute scales into the story. And now the interesting thing is this means that the principle of least action can't give you solutions if the scale, the root mean square length, the external scale, the extrinsic scale, is either zero or infinity at one of the ends, because then you can't form a proper ratio between zero or infinity and a finite number. So then the question is, are the Newtonian solutions for which the extrinsic scale is either zero or infinity at one end? Because then they can't be found by the principle of least action. But if they're Newtonian solutions, they are Newtonian solutions with his second law, as we shall see, not over the whole length, but they would be very interesting solutions. And amazingly, they were discovered. The first person who discovered it was somebody called Carl Sundman in 1907. So Carl Sundman asked, he said, I think I'm the first person to ask this question, in the three-body problem, are there solutions, are there situations into which three-point particles of arbitrary masses, but they can be equal mass, can collide simultaneously at a point, at their center of mass? And he showed they can. And it's absolutely fabulous mathematics. I don't think there's anything remotely like that mathematics in attempts to treat general relativity right at its Big Bang. So he showed they could. Now he showed that, and that would be that the root mean square length must be zero. The extrinsic scale must be zero. And he also showed that the angular momentum must be zero. And in the case of the three-body problem, he showed that the limiting shape, as they come to collide, the shape must become ever more perfectly either equilateral or be collinear. So when you time reverse those, although Sundman didn't think of doing that, and I think I might be the first person who suggested you should do that, if that's time reverse, that's a Newtonian Big Bang from on the face of it, what looks like all the particles sitting on a point, but in reality, shall we say, if the shape can be aware of itself, the shape is aware of starting as an equilateral triangle.
You mentioned in answer to Simon's question, you said that your vectors R were defined at the center of mass.
Yes, I'm referring, sorry, yes, it all should be relative to the center. Well, no, that's a simplification. It's not essential, but it's a simplification.
Well, the reason I'm asking is because is your Newtonian Big Bang in a specific position? Because in general relativity, it's not.
No, an equilateral triangle. An equilateral triangle is a concept in my brain as well as yours, and it can be anywhere you like. It doesn't have any position.
So
it's just a shape.
I mean, yesterday I said the Big Bang was everywhere in this room. Now, what about this Newtonian Big Bang? Was that in this room?
No. It's just an equilateral triangle. Period. Nothing more than that. Nothing less. It's just pure mathematics. It's an equilateral triangle.
Yeah, I think what Charles is trying to say is this is the three-body problem, right? And is this solution described that you have three bodies that form an equilateral triangle that are separating from each
Well,
other.
we'll come to the sense in which they get, in which you can say that the universe is expanding, but it's not in the sense that with respect to an external scale. It's with respect to an intrinsic scale, which I'm going to introduce.
Which doesn't have a position.
It doesn't. I mean.
Arbitrarily small triangles, and when you have everything coming together, a point that does not.
Well, to say they're arbitrarily small, you've got to have an external ruler. Then you can say it's arbitrarily small. If you haven't got that external ruler, if, so to speak, each vertex of the triangle could see the other two vertices, all it would see is the angle to them.
But you have L RMS equals 0. Doesn't that mean it's a point?
With an extrinsic scale. I haven't yet got to the intrinsic scale, which clarifies these things. No. Sorry, don't take it that I'm taking offense when you press me, but that's very important because I'm obviously not getting things across clearly. But this is a huge, I would say it's a huge neglected symmetry. I'm going to quote to you in a minute, later on, a passage from Poincaré, which is fun there. So only a year later, somebody called, I forget what his name is, but within a year, somebody had shown that this could also happen for an arbitrary number of particles. They could all collide at a point, and in all cases, the energy, the angular momentum had to be 0. The energy could be anything, and then. In 1922 at the latest, I'm not quite sure. So by the way, the time reversed, they're Newtonian Big Bangs, and this is 2 decades before Hubble's discovery. Yeah?
I don't understand why it's not completely obvious, these statements, that, I throw a ball up and it comes back down and it hits the earth. It's 2 particles and they collide. What's the... You're sort of enchanted by Sundman's...
Well, the thing is, with two particles don't define a shape.
And so with 3 particles, just by a sort of simple symmetry argument...
Sorry?
By a simple symmetry argument, if I have, when you told me that they would collide, I said, well, yeah, if it's an equilateral triangle and there's no angular momentum, of course they're going to collide. It doesn't seem...
Well, by the way, the shapes...
If they miss, they're going to miss in a certain direction that would break the symmetry.
That may well be, but what is much more interesting than the equilateral triangles is what I'll come on to, is when there's many more particles, and then the shapes are really very interesting, as I hope you'll see.
But the reason, so your objection was that why not 2 particles? Is that right?
No, I was confused as to why it took until 1907 to show that 3 particles, or even n particles in arranged symmetrically, falling towards each other, they have to collide. That seems sort of obvious. And
well, 0 means they all are on regular orbits. They have to.
Yes, that would be, but in fact, you'll see it gets much more interesting when we get up to about a few more particles than just 3 or 4. I mean, the regular tetrahedron is very similar to the equilateral triangle. Yeah?
Is this resolved with particles of different mass?
Sorry? They can have any mass. So it's with arbitrary masses. That makes it non-trivial. Yes, yeah. Yes. And the same goes. Thank you very much. The same goes for the regular tetrahedron. But that's restricted to there. By the way, these results were anticipated by Lagrange in 1772, but that would take me a bit away from things. Yes.
So there's 2 types of solutions, right?
Sorry?
There's 2 solutions, either equilateral triangle kind of shape, or collinear.
Yes, and by the way, the collinear is ultimately it's the explanation of where the James Webb Telescope is sitting, and that was discovered by Euler in 1663. The possibility of the James Webb Telescope, it goes back to Euler around 1763, sorry. Okay, so if I'll go on now if I may, but do ask questions. At the latest by 1922, but it may well have been earlier, Jean Chazzy, a very brilliant French mathematician who's the one in the middle, showed that 3 or more particles can get to infinity and be at rest when they get there. That's the analogue of just escape in 2 particles, a particle escaping from the Earth. But in both cases, now this is where it gets interesting, the final shape in both cases is very special. So the parabolic escape, where they all get to infinity, the energy must be 0, the angular momentum can be anything. So that's sort of dual to the total collision. And in both cases, the final shape must be special. Now, I'll come to that now. So now I introduce the concept of shape complexity. So I introduce this as follows. Suppose just a finite number of particles, let's suppose they're equal mass particles in Euclidean space, and you want a pure number, a dimensionless number, which characterizes the extent to which they are uniformly distributed or clustered. And if it's going to be scale invariant, it's the simplest way to achieve that. There are other ways. But anyway, whatever it is, the expression must have, in length, must have length dimension 0. So the easiest way that is to take a ratio of 2 lengths. And then immediately 2 lengths stand out. I've already introduced the root mean square length, which is dominated by the large separations. But the other one you can use is the mean harmonic length, and that's in the first equation there. It's the inverse of the Newton gravitational potential with the sign reversed, rather interestingly. So what we call the shape complexity is the root mean square length divided by the mean harmonic length. And for the case of equal mass, you see the expression for it there. And mass weighting is obvious. Now, I think it's very remarkable. So Leibniz was obsessed with there being variety. I was on the lookout for a quantity which characterized variety and came across this quantity which has long been used for 30 years or 40 years at least in n-body theory, which they call the shape potential or the normalized Newton potential. It's just the ratio of the 2 numbers that really does govern the Newtonian theory. And in some senses, it's that product of the 2, that dimensionless number, as I will explain, that really does govern the whole of Newtonian n-body problem when you've not allowed any contamination by absolute elements. So you'll see that it's all very holistic. So the total collision and parabolic escape solutions always end at a minimum or saddle of this shape complexity. And as yet, n-body specialists have found no way to continue the solutions beyond these points, total collisions. They can be continued, but there's no unique way to do it. There's infinitely many ways that you can continue it. It's because, in fact, there's an essential singularity in the theory at that point there. And then the other thing which shows how important shape is in all this, for this to happen, the solution trajectory in shape space, so shape space is the space of all possible shapes with a given number of particles, it has a landscape on it which is defined by this shape complexity. There's an altitude on it. And they can only get to basically, except if the particles are all equal mass, these solutions can only get either to parabolic escape or total collision if they approach that minimum or saddle along eigenvectors of the Hessian of the shape potential, the determinant of the second derivatives. And the great bulk of them come in or go out along the eigenvector with the largest eigenvalue. So that's a fact of how really Newtonian dynamics, properly understood, is about scale invariant quantities. And completely impossible to understand its subtleties without. Now, yes, I've got it. Oh, yes. Now I'll tell you about central configurations. So central, yes.
Before going there, is it possible to know two different shapes with different shape complexity? Shapes we can imagine.
Sorry, given any distribution of particles
Yeah.
and their masses, or their mass ratios, which is all that counts, the shape complexity is uniquely determined.
Yeah. This I understand, but like, I would like, if it's possible, if not, like, I can do it later. How can I imagine one shape being more complex than another according to this measure?
If they have the same number, if there are the same numbers of particles with the same mass ratios, then that number just tells you. There's a given number of particles with given mass ratios, that defines what I call shape space, and shape space is foliated by values of the complexity.
Yeah, that makes sense mathematically.
Yeah.
What I would like to have is more of a pictorial intuition of what complexity means here. In the sense that, can you say that if an equilateral triangle of equal masses is more complex, or is it less complex than an isosceles triangle?
It's less complex. The equilateral triangle for any mass ratios is the minimum. It's the absolute minimum of the complexity. The minute you get either isosceles or scalene, the complexity goes up. And as it gets more and more scalene and more two particles relatively closer to the other, it goes unbounded. There are infinite peaks of the complexity.
Okay.
Yeah.
Are these flat triangles, or are they curved?
In the three-body problem, if the angular momentum is zero, it's planar. That was proved by a German called Jobbik in about 1880, I think.
Just to have a bit more intuition. So then if n equals 4, if I have a configuration that is not coplanar, then the shape complexity is higher.
I guess so. I mean, by the way, I'm coming on to central configurations, which is a topic of very considerable. It's a major unsolved problem in mathematics to do with how many of these things there are. So let me come on to them, perhaps, if I may. Yeah. So a central configuration, which was also coined by that German I mentioned just now, Jobbik, in 1899. A central configuration is one where the net gravitational force acting on each particle, exerted by all the other particles, points exactly to the center of mass of the complete system, and with a strength that increases linearly with the distance from it. So one way of thinking about a central configuration is that if you held the particles at rest in that, they would then fall under gravity until they all collide together. So that's one definition of a central configuration. But it's better to think of it as a relative equilibrium, because you can balance those gravitational forces by repulsive Hooke forces, and that's the way there's a lot of discussion about that of relative equilibria. And in 2 dimensions, the forces can be balanced by centrifugal force. And that's actually behind the theory of the James Webb Telescope, where it's sitting. And also, very incredibly beautifully, it's behind Saturn's rings. Saturn's rings are a central configuration. And one more thing. After J.J. Thomson had discovered the electron, and before Rutherford had done his scattering experiments with alpha particles, his main effort to explain atomic structure was with things like central configurations, relative equilibria. So there's quite a pass back there. And my wildest guess is that maybe Thomson was onto the right thing. Quantum mechanics might just not be right. Anyway, so there's a very good article on central configurations in Wikipedia at the moment, the Lagrange points and Saturn's rings. And as I say, central configurations are critical points, minima or saddles of the shape complexity. And just give me a set of particles with their mass ratios, and that completely determines all the central configurations that they can have. And another thing which is very interesting about them, there's a huge number of them. They're essentially, if they're collinear ones, you can immediately show they're factorial in number. So it's an unknown, they may be infinite in number, but they're certainly factorial in number. So this is just huge number of shapes, and I'll show you some incredibly rich structures that they form in a moment or two. And it's clearly a very holistic concept because it's just determined by the mass ratios, and the mass ratios determine the relative separations between the particles. So the complexity has many roles. First of all, it measures complexity or variety, as I've just described. Now, the interesting thing is it's a scale-invariant potential energy, because that's what it is, a potential energy. It's the product of two potential energies, and it is that. And as we'll see, the critical points are very special structures. I've already mentioned that in the 3 and 4 body problems. But it's an intrinsic scale. Now I'm going to contrast an extrinsic absolute scale with an intrinsic scale, because the shape complexity is the root mean square length divided by the mean harmonic length. And the large separations dominate the root mean square length, and the small ones dominate the mean harmonic length. So if I want to measure a long interval, I take a short interval and see how many times it goes into it. So basically, if you want to say you're talking about the size of the universe in intrinsic terms, or at least of a Newtonian universe of a finite number of particles, it is the quantity to choose is precisely the shape complexity. That is an intrinsic scale. So I think that's pretty interesting. And now the other thing is the intrinsic scale and the extrinsic scale can behave very, very differently, and they do this particularly at the Big Bangs in these Newtonian theory, because the extrinsic scale goes to 0, but the intrinsic scale goes to a finite value. It's the absolute minimum. The shape complexity is a positive definite number, and it has an absolute minimum, which is, by the way, the most uniform shape that the universe can have of those particles. So it goes there. And I'm now going to show that this quantity defines the direction of time, and I think casts huge doubt on a lot of talk about entropy of the universe and what is really determining the arrow of time, the experienced arrow of time. Let me just tell you about that. So this is a paper that was published 10 years ago, Flavio Mercati, Tim Kozlowski, and myself. And basically, first of all, I'll tell you about a Janus point, which is not where there's a total collision. Lagrange in 1772 showed that in the 3-body problem, in the infinite, if the energy is non-negative, either 0 or positive, but also, in fact, effectively in many cases if it's negative as well, in the infinite past, the size is infinitely great, the root mean square length infinitely great, comes down monotonically to a finite value, and then increases monotonically to infinity. And that existence of that Janus point of minimum size, I call it a Janus point because if the Roman god stood there, he would see the size increasing in both directions, and that defines bidirectional arrows of time. And that unique point there is nothing whatever to do with me putting in by hand the existence of that point. It's there as a direct consequence of Newton's laws. Very simple. It's a 2-line proof which relies on Newton's second law, the fact that the Newton potential is homogeneous at degree -1 and is negative definite. and it's a two-line proof. And Lagrange found it there. Now, but that's not something that creatures within such a universe can see, because they don't have an external ruler. What they see is what the universe looks like. And what it looks like at near that minimum, the Janus Point minimum, it's like a swarm of bees. It's typically the most uniform distribution in the whole history of that solution, and random and pretty good approximation to thermal velocity. Simon?
What do you mean by most uniform? What's the measure of uniformity?
Precisely this quantity. The complexity has its minimum value, not exactly at that point, except by fortuitously. It's in the vicinity of it.
And I'm just thinking this through, right? So that C is scale invariant. Sorry, you've already said this many times, I'm sure. Right?
Yes.
C is scale invariant. So it isn't sort of how compact or spread out it is. It's something a little bit harder for me to grasp.
No. It's in the shape. It requires sorry.
I'm just curious, like if you were just to draw a shape with high C and low C, what would those shapes look like?
Well, the simplest one is the low C is the equilateral triangle, and the high C is one where there's one point here, and the two others are very close to each other compared with the distance there.
Or isosceles or something. Yeah. Very, very isosceles.
Yeah, it's very isosceles, or very pointed, yeah.
Yeah, sure. Does it look like a Jackson Pollock? Like, is a Jackson Pollock painting high C? And I'm joking a little bit, but I'm trying to translate that notion of complexity into something that's a little more comprehensible.
Sorry?
Does it have to do with convexity? So if we have a convex polygon, is it more less complex than a spiky?
Sorry, I didn't catch one word.
Yeah, sure. So if I have n particles in a plane, that's focused on the plane. If I have a convex polygon,
Yeah.
is that less complex than a polygon where it's like a star?
Almost certainly at a guess, but without actually doing the calculation, I wouldn't like to stick my neck out.
Okay.
But the good thing about this is there's absolutely no shadow of doubt about it. I mean, either it's a central, the complexity is just fixed once and for all.
I understand that.
Yeah.
I'm just trying to imagine it.
But then the thing is, as you go away from the Janus point in this picture, subsystems form. So the total universe has vanishing angular momentum, and in Dirac's term, it's described by constrained Hamiltonian dynamics. When you get out, little subsystems form, isolated, and above all, they can be Kepler pairs of two particles going around each other. And as you go further and further away from the Janus point, it gets ever more ordered and regular. So you get a whole host of two-particle systems, which are each in themselves are rods, clocks, and compasses describing, and they're all mutually synchronized. They're not the same periods, but the ratios of the periods tend to be ever more constant ratios of these things like that. So as you go out from chaos to order. This is the exact opposite of entropic effect, as the way one normally thinks about it.
Julian, what's the x-axis on the plot on the top?
The x-axis could be time.
Could be
time, yes. Yeah, it could be time, yeah. The idea is just that the complexity increases like that. And it's purely dynamical.
It increases it with respect to some variable.
Yes,
That
or...
variable is probably time.
Well, I could introduce ephemeris time. I mean, it would increase relative to ephemeris time, that quantity that I mentioned earlier. And in fact, my collaborator in California, Hemant Shukla, has done these things where he's plotted the growth of the complexity against ephemeris time, and it starts with the complexity fluctuates a lot near the Janus point, but then they go up with the same slope from then on.
But we're not to imagine that Janus Point is in a point in space. Is that right?
No, it's a relative point. It corresponds to a special shape.
Okay.
No, sorry, that's not quite true. the minimum of the complexity is a special shape.
Now in the diagram, the second diagram, you had something spread out and then something compact and something spread out. Are those, can we say that the Janus Point is in some sense smaller than the spread out thing? Or what is the scale of the distance here that is spread out in?
It's spread out in terms of what, so to speak, creatures within the universe can see. So when you look at when you see stars on the sky is always whatever it is, what's the area of the 4 pi, isn't it? The sky is always exactly the same size. It's just a question of whether the stars are more clustered together on the sky. You can imagine the same 4 pi sky, that's a dimensionless number, a 4 pi sky, and you could have stars very uniformly distributed all over the sky, or they could be clustered in like we see in constellations.
So could you have drawn that second panel with a larger thing in the middle?
Yeah.
That has no significance. It's scale invariant. I mean, it would just look exact. It would just be
misleading, I think, to show that point, the things coming together. That's sort of misleading, right? You could have shown those 3 figures with the little bee swarm is exactly the same size on the screen, and it would be fine, right?
Sorry, is this an earlier slide or
the slide we have here? Yeah.
the slide here?
I think.
Oh yes, sorry, yes, no. Every size that you see is purely nominal. What is not nominal is that what is not nominal or arbitrary is that that one of these things is bigger than that, because there's a ratio, there's a meaningful ratio in that size there. That is meaningful. But overall, it's scale invariant. It goes back to what I was saying about the Chinese characters. Their meaning does not depend upon their size.
I think what Charlie's objecting to, maybe or reacting to, is that swarm of bees in the center there looks smaller on the screen than the 2.
Yeah, no, this is unfortunate. Yes. No, that's a good.
Very unfortunate. For Charlie.
Yeah, very unfortunate. Unfortunate, it's now called an iconic diagram. But it's no. I mean, it's just. Excuse me. Can you get my thing? I'm just going to read you something of Poincaré at this stage, because I think it's too good to miss.
It has to be cited at this part of the lecture.
You what?
Poincaré has to be cited at this juncture of the lecture.
Yeah.
Point about where is it? Where are these objects? Because you're wrong. I assume what Julian is meaning here is that there's some kind of equivalence class. You have configuration with.
It's equivalent. Yeah, that's a good equivalence class. Yeah.
So it's like you can imagine an absolute space, and you have the configuration somewhere. If you have the same configuration elsewhere, so center mass is just displaced, then you have the equivalence class of all those cases. So you kind of quotient out the underlying absolute space so that nothing depends on it, and you're only looking at the kind of intrinsic attributes.
Yeah, such a 3-dimensional space.
Yeah.
Confusing.
So this is from Poincaré's Science and Method, about 1908, published. Suppose that in one night all the dimensions of the universe became 1,000 times larger. The world will remain similar to itself if we give the word similitude the meaning it has in the 3rd book of Euclid. Only what was formerly a meter long will now measure a kilometer, and what was a millimeter long will become a meter. The bed in which I went to sleep and my body itself will have grown in the same proportion. When I wake in the morning, what will be my feeling in the face of such an astonishing transformation? Well, I shall not notice anything at all.
That's not what J.B.S. Haldane said about this.
Well,
It's a well-known biological problem that things are scale variable.
well, but that's maybe because the Earth sets a scale. It's like quantum. It's like thermodynamics and statistical mechanics in a box.
It's sailed by how strong the gravitational force is. That's the main constraint on, for example, the shapes of animals like a fly or an elephant. They are not independent of the gravitational field in which they live.
That's right. But by the way, actually, in the Newtonian n-body problem, the gravitational constant really doesn't appear in it at all. It's all about mass ratios. And in fact, the gravitational constant as a constant only came in when Cavendish wanted to work out how much mass there was in the Earth compared with, in, say, Ben Nevis or something like that.
Kepler pairs there, and those Kepler pairs, how tight they are, how fast they're going, how strong the gravitational field is that's maintaining them, and the Kepler pairs, that changes from one Kepler pair to another.
Yes, but that's to do to the mass ratios, because everything, I mean, Newton is all in terms of mass ratios. It's all in terms of mass ratios. There isn't really a gravitational constant. It's just a convenient way of thinking about things.
It's just the parameterization that you would use. So the notion of time that it would take for you to follow within the Newton.
Hamiltonian constraints, I don't know that clarifies certain more.
Where did I put that point? Oh, it's here. The comment I want, I mean, first of all, it's very entertaining, that passage in Poincaré. But the other thing which is amazing, here's one of the greatest mathematicians of all time. He never did anything about it. He didn't look for something which is scale invariant, not to my knowledge. And lo and behold, it was just in the very year that book was published, the quantity that is significant was appearing in that work by Sundtmann.
No connection to his recurrence theorem?
No, because the recurrence theorem this is the key thing. This is why I'm very skeptical about all talk of entropy associated with the whole universe. So entropy is meaningful if the solutions of your dynamical system only explore a phase space of bounded Liouville measure. This is made absolutely clear by Gibbs in his book. He says, if the system I'm considering can explore infinite space, or the momenta can grow without bound, everything I say becomes meaningless because I can't define probabilities meaningfully. And very few people notice that. And the thing is that the first and oldest dynamical theory has an unbounded Liouville phase space in the normal way you think about it. That's the Newtonian n-body problem, because the root mean square length becomes infinite. And there is a complete theory of statistics in that case, which my collaborators and I are, so far as I know, the first people who are exploring. It has never been done before. And people just have been completely unaware of its existence.
Do you know if this is linked with the notions of entropy as a measure of information for infinite dimensional systems?
That's beyond my pay grade, I would say.
I'm asking.
Sorry, say.
So I come from information theory, and we have the Shannon information measure, and that is related to entropy in the quantum mechanical.
Can I immediately come in with one point?
Yeah.
There's of course only a finite number of characters in the alphabet.
Exactly.
So that's the bound, that's essentially your box in which your system is there.
I agree. However, there have been attempts to define entropy in the same way as Shannon defines it for finite dimensional systems, for infinite dimensional systems.
Oh, well, I'm not aware. Well, perhaps we might talk about that.
Okay,
yeah.
that's why I was asking if you.
Yes, no, I'm unaware of that. All I will say is there's been an incredible neglect of when the system can explore an unbounded phase space. And it all goes back to, I think it's just historical inertia. Thermodynamics was discovered through the study of steam engines. If the steam escapes from the cylinder, the steam engine stops. And Boltzmann questioned whether in his famous debate with Zermelo, does the universe have a bounded phase space?
Famous debate with who? Famous debate with who?
Zermelo in 1896. But after that, I'm going to stick my neck out and say, I think I'm the first person who really stuck my neck out and said, is the universe in a box? Is that the right way to think about these things? And I get more and more hopeful that it's the wrong way, thinking that it may be the wrong way.
Not in a box. Not in a box. Not in a box.
Well, you can put it in a box.
No, you shouldn't. You shouldn't.
No, but like, you can use causal compactification, for example, and then like you can try to study it there. Like, you can use
Yes, I'm not quite sure.
You know?
I'm not quite sure whether that's really the right way to do it, Kosher.
Yeah, I agree,
Yeah.
but my point is like conceptually we don't think about it that way, but we have, like some tools have been developed to treat space-time using causal compactification.
Oh yes, yes. No, no. I'm aware of that work, and I've never sort of looked at it from this sort of perspective. But and I mean, I have twice spoken in a seminar in front of Roger and pointed out that this special point, the Janus point, not even the Big Bang things, that they're there of dynamical necessity, and Roger just says, no, you're putting them in there by hand. So you can't win on those terms.
But the scale invariance that you've been talking about is very important to his cyclic universe model, right?
Well, yeah, but then then he suddenly says the scale changes, and my original draft, when I was asked to review his book, I said this smacks of the divine intervention, and then I changed it to stretch his credulity. Yeah, go on.
I have a question now.
Of course.
How do you define subsystems here?
What?
How do you define subsystems?
When in the Newtonian n-body problem, as they become ever better, you can describe them ever better by Newtonian gravity in an inertial frame of reference in which they have to ever better accuracy, energy, angular momentum, and momentum that are conserved.
Okay.
Yeah, and that comes straight. I mean, I'm seeing beautifully this man who works with me in California. He's doing numerical stuff. It comes out just like that.
One of the nice things is that you get the background.
No, yeah, but I was just curious if it was something like you select a group of particles that locally they have angular momentum 0.
Well, they can be, that's a nice thing, I think, right? Because locally, the angular momentum doesn't need to be 0, even though the totality of it is. So that's kind of how you get Newtonian mechanics.
Okay.
But the of all of the subsystems must add up to 0, and the energies, yeah.
You know, in a shape, right? So, I mean, in these shapes you've drawn here, for example, some points are sort of nearer to the edge of the shape than others. Is that fair?
Yes, yes. I mean, they're further from the. I mean, the center of mass is always well defined in the shape. If you know the masses, yes.
So why does the universe look homogeneous in every direction to us?
Well, I don't know whether we'll get onto that this evening, but I think the other thing I think is there's something incredibly special about the 1/r forces. We were talking about this before, and 3-dimension of space. The only circumstances under which the Newton potential theorem holds that if you have a spherically symmetric distribution of mass, a body outside it feels a force as if it was all concentrated at the center, and a body that's within it feels only the mass that's within that radius. And that is unique to 3-dimensional dimensions and the 1/r² force law. And I'm coming to think that this may tell us an awful lot about the universe and actually lead possibly to the holy grail of cosmology, which is to show that the cosmological principle should be satisfied, that take a large enough region, you will find the cosmological principle holds.
Why do we happen to be, why do we happen to be at a point in the shape? Like we're at some point in this shape, right?
Well, let me go on to one or two more slides,
sure.
because they. So this is just to show my collaborator, Tim Koslowski. You'll be seeing this, Simon, soon. I have a very special desk, and that's my study there. And we call it mission control, or I called it mission. No, a friend of mine called it mission control. So here's an early stage of a 4-particle Big Bang. I was talking about this man, Hemant Shukla, in California. So this would have started off close to a regular tetrahedron, and it's 4 particles, and you see very soon a Kepler pair forms, and 2 particles go off, and one of them goes off so fast that it's out of the picture, sorry. Wait a minute. It's out of the picture up there, whereas this one is here relative to the Kepler pair. And that system there, and Hemant in California is getting results like this with, he starts with 50 particles and he gets 11 Kepler pairs, and in one case he got a remarkably stable three-body system with one particle threading a Kepler pair. And so you see there that is the exact opposite of entropic behavior. It's very chaotic motion at the start. And that's all a direct consequence of Newton's laws. There's no past hypothesis of explaining the second law of thermodynamics. I mean, Feynman was the first person who said, to understand the second law of thermodynamics, we have to add something which is not in the laws of nature, that there was a very special state in the past. And then David Albert in New York, Columbia University, called that the past hypothesis. That's absolutely not necessary in Newtonian theory, and I strongly suspect, I think it's a big question mark whether it holds in general relativity as well, because in many ways general Newtonian theory does so well, matches so well general relativity.
It seems to me that doesn't make sense because we do not have a relationship. We cannot define entropy in terms of gravity. Some people think that when you fall down, like those two pairs, they're getting tighter. As they make those other 2 points go away, they're getting tighter. And so the question is that increasing entropy or decreasing entropy? But you need a definition of entropy in terms of gravitational collapse, which we don't have, unless you just want to say a black hole entropy.
Well, I think perhaps why don't we talk about that after, because otherwise, because I think this, if we're not going to be thrown out, let's press on a little bit, but there.
Just, sorry.
Yeah, no, go on.
To the slide.
No, go on.
Do you have strong numerical results that this is the expected behavior? That if you start from a stable configuration, at least some of the particles.
Sorry, if you do what? If you start from
a tetrahedron or like one of these.
By the way, you can't start from a central configuration. This is very interesting. This inverts ideas about causality, by the way. So it's nothing if not radical, these things. But sorry, what was your question?
Yeah, sure. But if I understood you correctly, you said in this slide the initial configuration was a very low genus shape.
It was close to a tetrahedron,
Exactly.
a regular tetrahedron.
Yeah. So what I'm saying is this the expected behavior? That if you are close to one of these central configurations, that one subset of the particles would zoom off with respect to the others?
There will always, so this is another result of if the energy is non-negative, the root mean square length will always grow to infinity. That was proven by Lagrange. So there will always be at least one particle that escapes to infinity. That's been known since Lagrange's paper in 1772.
Could you point out where the tetrahedron is?
Sorry?
Could you point out where the initial tetrahedron was?
No. Anyway, I mean, he's just given me these things, and you can't actually. I'll go on to why you can't actually start it at a tetrahedron going out along one of the eigenvectors. It's because there's an essential singularity in the data. There isn't a proper Cauchy initial data for these things. So, in fact, what you've got only becomes clear as the solution develops. Perhaps I go on if that's okay. So, next one. Let me now show. So, the complexity is positive definite, and in virtually all cases it has a unique minimum. And in 3 dimensions, uniquely in 3 dimensions, it's incredibly uniform and spherical if you have a large number. This is the central configuration, what I call alpha. It won't be the exact minimum because that's there, but it's very, very close to the absolute minimum. This is one of 5,000 particles, and you see, and there's a section on the right is a section through it, And you see that basically it's a very uniform distribution. And the more particles you have, the more it is. And this incredible uniformity and sphericity is entirely due to Newton's potential theorem. It's unique to 3 dimensions. And so basically, if you imagine little bugs inside that thing, the separations between the particles are your rulers. So that this is... The Newtonian theory is defining its own rulers and its own clocks to measure what it's doing. It all comes out of Newton's second law, the law of gravity, and eliminating all contamination by absolute elements. And these things are so this was things like the one on the left, the spherical thing, that's been known for at least 25 years or so, and had been suspected long before. But there's a very nice numerical paper from 2002 by Batty, Gibbons, and Sutcliffe. So it's never perfectly uniform. Now the next thing is you've got these total collision solutions which you can time reverse, and then they become big bangs, but there are also parabolic escape. And in both cases they must start at one of these special points.
Hyperbolic escape?
But you can have hyperbolic escape, but it won't be if the energy and angular momentum are zero. Then it's not. Then they all stay together. They get infinitely. They spread out, but it's not hyperbolic escape. The shape goes on changing forever.
But can't these particles exchange energy and angular momentum in there because of the gravitational interactions, and then one gets thrown off hyperbolically? Just like, for example, stars in the galaxy. Stars go zooming out because they were in tight configuration, 3 bodies.
Yes, but we're getting into.
Okay, forget it.
I think, yeah, all right. So, but now this is what is, I think, very, very interesting, because a paper in 2009, which is given here, what they showed is they expressed it entirely in Newtonian terms, from any configuration of the system, for any number of particles, there's always a parabolic escape solution to the thing that I call alpha, the absolute minimum of the complexity. And it has other splendid properties. It minimizes the action over any finite length of the solution, and there's no collisions in it. Now, you could time reverse that, and it would look like, well, the shapes would be, I think, just the same as if it was a total collision time reversed. So if the energy and the angular momentum are both zero, and it's either a time reverse total collision or a parabolic escape, and I'm only giving you the shapes, can you tell in which direction the Newtonian size, the root mean square length, is increasing? Because if you can't, it means that that scale has no meaning at all. Now, I've discussed this with this friend of mine who's a very highly regarded mathematician at the observatory in Paris. And he said, I can't see anything wrong with your argument, Julian, and I suspect you're right. So I'm putting this forward. But if this case, it says that Newtonian gravity, uncontaminated by its absolutes, is not only time reversal symmetric, but scale reversal symmetric. So that's a new symmetry. If that's right, that's a new symmetry of Newton's equations. And also also let me mention about the etymology of perfection, which Leibniz pointed out. It's complete. It means perfecere, to complete. So what that means is that it's a complete set of solutions that go from the most uniform shape. If you're just given the shapes, you go from the most uniform shape to any other shape imaginable. And in principle, it would mean that if you just approximated our bodies by point particles, there is a Newtonian solution from the absolute minimum of those point particles to where we are now. It's as productive, as fecund as that, the thing there. So there's a caveat about that. This property may hold for other central configurations and not necessarily for alpha, but it's been proven to be the case for alpha. So that's what I'm saying. So that's just what I'm really saying. So a total collision, the angular momentum must be zero and the energy is free. In parabolic escape, the energy is zero and the angular momentum is free. But if both of those conditions are satisfied, are those solutions indistinguishable as a succession of shapes? If so, all Newtonian absolutes are meaningless for internal absolutes. And moreover, so unadulterated Newtonian gravity is both time and scale reversal symmetric. And the other thing is there's increasing numerical evidence we're finding that in these circumstances with both energy and angular momentum zero, and going from close to alpha, you create more structures. Each individual, there's lots more solutions with interesting properties. There's vastly more interest being created under these circumstances. So my feeling is that Newton inadvertently and there's historical reasons why I introduced absolute space and time and with it absolute scale, he put the most incredibly creative system in a box and prevented it from showing all its great creativity, the thing there. I think it's quite remarkable. So let me show you again what it is like with the next slide. So Newton, oh yes, so what did Newton say of the solar system with all the planets going around, so all in the same direction and all the satellites at that stage known to be going in the same direction. It is not to be conceived that mere mechanical causes could give rise to so many regular motions. This most beautiful system of the sun, planets and comets could only proceed from the counsel and dominion of an intelligent and powerful being. Now, Newton says explicitly that God started the solar system in a system like that, and then because the planets would perturb each other, every now and then he would have to intervene and put them right back in the right order. Fairly soon, people like Laplace and others, I think, had shown that it didn't disrupt nearly so easily as Newton had thought, but it still might. But no, Newton's theory creates all possible shapes out of maximal uniformity. It's far more creative and wonderful than Newton realized. Now look at this structure. Now this is creation of structure. So on the left, now in 2 dimensions, Newton's potential theorem doesn't hold. So on the left is very close to minimum complexity, but you'll see that the separations increase as you go to the rim of the disk. And that was not unexpected. Now through my great interest in Newtonian gravity, Alain Albuy in Paris, the mathematician, put this Spanish student, Manuel Izquierdo, onto finding some central configurations. And just by chance, he did something which nobody had done before. Most physicists are always looking for the absolute minimum of something. They're not looking for something that's a bit away from it. So they'd had programs which explicitly stopped them finding local minima and saddles above the absolute minimum. But by chance, this chap had programs that actually found central configurations about only 1 or 2% above the absolute minimum. And he found these incredible structures like that. Absolutely amazing structure. And Alain sent me an email. He's finding lines. He meant he's finding filaments. But this was a big surprise to the top n-body specialists in the world. And people are still wondering about quite how these structures form. So I think that's quite interesting. And also, again, I was delighted when I finally got round to looking up the etymology of creation. It's not from creation out of nothing. It's from the Indo-Germanic word ker, to grow. So this on the left is like sort of well-tilled soil, and on the right it's plants growing out of it and eventually becoming oak trees and things like that. Simon, you have a question?
I'm curious. I mean, in the pure n-body case, right? There's no pressure. Particles can get arbitrarily close, things like that. I'm just wondering, do these results stick around approximately if you allow for non-gravitational forces?
Well, this is very early stages. We're thinking of adding electrostatic forces and seeing what's happened. By the way, I mean, I've already mentioned that both Tim and I are seriously exploring whether quantum mechanics needs a wave function or a Planck's constant. If it's scale invariant, I don't think there can be a Planck's constant in it because it's dimensionful. So Planck's constant must be emergent. And Tim was the first person to point out that there's a really wonderful generalization of Boltzmann's idea about the Boltzmann formula for entropy. So Boltzmann in 1877 said, molecules in a box, there are vastly more uniform distributions than non-uniform distributions. And that eventually transformed, he didn't write it down, but somebody else did, that the entropy S equals K log W. That's where the entropy, the expression for entropy comes from Boltzmann's idea. But now, so my idea back that you'll find in the Janus Point is that the complexity should be an internal time. It foliates shape space. So each foliation isocomplexity surface could be called, well, it could be called the age of the universe. You take away the absolute minimum, and then the difference between them is the age of the universe. And then interestingly, that difference, you could also say, is the amount of scale invariant potential energy that had been used to create that structure. That's a pretty interesting way. But then you say, if I insist on time advancing and time is complexity, how can that happen? Well, the easiest way is just to put a few of the particles in the shape on the left closer to each other. That will increase the complexity. But it violates the cosmological principle. Then you remember Boltzmann's idea and you realize that there's vastly more ways to increase the complexity by changing all the separations a little bit. And actually, before Manuel discovered his amazing one there, I had predicted that all the smallest separations would be the same. And they are. They are on the left, except for this two-dimensional distortion, but in 3 dimensions they're all the same. And they are. Now, I was thinking that this was a bit like, thinking in terms of quantum mechanics, that this was a bit like the Bohr condition which stops the electron falling into the proton. But Tim said, no, much better is to say that this is mimicking the Pauli exclusion principle. You're just getting the effect of the Pauli exclusion principle. You're mimicking it. So I think that's thought-provoking. So the next thing is, and Tim pointed this out, is that there's, the Newtonian configuration space is unbounded, and the root mean square length can grow to infinity. But when you quotient by dilatations to get to shape space, you've got a compact space. And on that compact space, there's a uniquely defined metric, what I call the natural metric or the best match metric. And that means you've got a probability measure on shape space. And this is this nice problem which Lewis Carroll, Charles Dodson here in Oxford, claimed he knew the answer to. Given 3 points in arbitrary positions in an infinite plane, what is the probability that they form an obtuse triangle? He claimed to have the answer, but it was soon found that it was wrong. You have to specify more conditions. So our conditions is that it's this measure that's defined unique. It comes uniquely. This measure on shape space is uniquely defined, or uniquely singled out. And in fact, actually, then it came to light that a collaborator of mine, Edward Anderson, had actually solved, and there's quite a long history on Dodson's problem, and that they give conflicting different results because they make different assumptions. And most of them, I think quite a lot of them settle around, is it 2/3 or something like this? But anyway, Edward Anderson, a collaborator of mine, actually about a decade ago published the answer within shape dynamics. It's 3/4, 75%, the probability of an obtuse triangle. It's unambiguous in this thing there. And you can, within certain limits, you specify certain limits on what the shape is like, say that the most acute angle in the triangle, say, but this can be applied to any shape, the most acute angle in the triangle lies in a certain range. What's the probability of finding a triangle like that? Unique answer in shape space. So I had set out to find what I thought would be Newtonian quantum gravity, which was a time-dependent Schrödinger equation on shape space. And our conclusion is you didn't need the wave function or the equation because there's a pre-existing Born density on shape space. Now, whether this can really do all of the incredible things that happen with quantum mechanics, but it's thought-provoking. And what is the implication of the fact that that there are probabilities, there's a probability density on possible shapes? It's there. So I'm wondering now, did Sundman back in 1907 stumble on the principle of creation? You say you start with a minimal complexity and then you require the complexity to grow, and then structure will form. So that's, I'm getting very near the end now. Oh, by the way, this is interesting. So one of the questions is how much of shape space is occupied by interesting shapes? Now, this is one which is not a central configuration. Emmand in California found this one, and he's dedicated to me. He calls it the broken heart. Somehow or other, his program stopped before it got to a proper central configuration. And he tests whether he's really found it, because he then thinks, if he thinks he's got it, he then lets them fall under gravity. And if they fall together, that's fine. But this thing, when he did it with this, he made the most appalling spaghetti mess and so forth. But what a shape! And so this is for 100 particles. So there's basically 100 factorial particles that are shapes that are central configurations, and then there's a huge area all around them because they're at critical points. So the whole lot of those shapes are surrounded by ones in shape space which are of similar structure. So there's one hell of a lot of damn interesting shapes in the Platonic realm of possible shapes. And I think I'm really very close. Oh, this is just to show you how this is again, the etymology of creation is to grow. This is typical early shapes of 100 particle in 2 dimensions. So top left.
Are these particles attracting each other gravitationally?
Yeah, these are subject to Newtonian gravity, basically.
And what's this? I'm looking at a 2-dimensional space on which they're...
This is 2-dimensional Newtonian gravity with the 1/r potential.
So this doesn't look like anything that would be familiar, because there should be Kepler pairs.
Oh, this is very, very early in the proceedings. This is very, very early in the proceedings.
And you've defined the initial conditions so that they are, looks like very, very...
Well, first of all, this is not the result of a numerical simulation. These are actually central configurations with increasing complexity and increasing age as I defined them. And so all I'm saying is that as the Newtonian solution evolves from alpha, which looks like top left, it will typically pass through shapes that are more or less like what I'm showing you there. And you see how the complexity grows, how the structures get ever more intricate. And 1 or 2 are really quite remarkable. Look at the... this one here, I think, is look at those 2 arcs there and this nearly perfect circle. I mean, Simon, there's something pretty marvelous about the most basic mathematics you can have in Euclidean geometry. That somehow or other it's creating these things.
Well, you must have put a condition on they're in these initial conditions that...
No, there's no... By the way, the initial condition is not under your control. It is absolutely... The theory predicts... By the way, these central configurations, they go out along the great bulk of them go out... They all go out along eigenvectors. And the great bulk of them go out along the one that's got the greatest eigenvalue. And initially, There's a central configuration. They hug that direction so tightly that you cannot distinguish them. But then when they get a bit further away from the central configuration, they splay out in all directions. And if, in the conditions of that theorem I told you, they will go to every single conceivable shape that you can imagine. They will all go out there to that, and they will just pass through that. And in fact, it inverts causality because you need a finite amount of the solution before you can begin to say what the solution is. So it's not the case of the past with normal Cauchy data determining the present. The present tells you what the past could be like.
What fraction of what you just said is responsible for the apparent anti-correlation between these points?
Anti-correlation.
For example, in the top left, they are absolutely spread out as much as possible. They're not pairing at all.
Yeah.
Those points are not random on that disk.
Yeah.
They've been defined to be away from each other.
Yeah.
Anti-correlated.
That
Function of that distribution.
that is what Newtonian that is typically what Newtonian theory in 2 dimensions, but it'll do the same sort of thing in 3 dimensions. We can be sure of that. That Newtonian theory just says that is what will happen if I don't allow any absolutes in my theory. I just get rid of every contamination, and then you just get these remarkable structures. And later on in the evolution, Kepler pairs will form, and you'll be able to measure expansion rates and things like that, and it will agree with ephemeris time.
So if I set E to 0, L to 0, those are my conditions.
Those are the conditions, and also that it comes from a central configuration, and preferably from the one that's the absolute minimum of the complexity, which is distinguished, I mean, by the principle of sufficient reason. It could come out of other ones. In fact, these are all central configurations. They could all be the initial thing. But I mean, Newtonian theory says there must be an initial shape of the universe, and it tells you what the initial shape will be like, and it will tell you the generic way, the characteristic way in which the shape will change. That's all in Newton theory.
If I lay down random points that obey E equals 0, L equals 0.
Well, you've got to give them velocities to do that.
Right. Okay.
Yeah.
But so if I lay down those points and I run that simulation long enough in one of the 2 directions, I'll hit a 0, or hit a minimum of C, right?
A minimum of
C of the complexity. Shape.
You will, yes, you'll almost certainly hit, in one way or another, you will pass through a Janus point, because you can't hit it would require such fine tuning, you couldn't possibly hit the central configuration and actually do that. Yeah. You will pass through the Janus point, and you will see the distribution of the particles getting more uniform, and then it will spread out more.
Yeah. I thought that C was conserved.
Beg your pardon?
I thought that the shape complexity was conserved.
No, it goes down, it goes up.
Right? In a Janus point, it does. In a Big Bang, it starts minimal and then increases from then on, with fluctuations. But if there's many particles, the fluctuations don't really show up.
So when is it conserved?
C.
So in general, it's not conserved.
No, it's not conserved.
It's not what?
C is not a constant.
No, C is absolutely not a constant. It grows. That's the eternal creativity of the universe, in my view.
It's supposed to be tiny because it grows within bounds, right? It grows within bounds, right? It can kind of oscillate a little bit.
It will fluctuate, but if there's sufficiently many particles, after a while the fluctuations have become relatively small.
Before that, there's these, because that's why I remember from last we discussed this. There's these bounds within which, so there's the shape complexity, and it kind of goes up and it won't.
Well, if there can be very sharp peaks. I mean, Hemant Shukla is finding sharp peaks early on, but then the question is, once the system has formed, is formed well-formed isolated subsystems, then the fluctuations, it's the fluctuations in the mean harmonic length in Newtonian terms that do the damage, cause these peaks, but that settles down after a while.
Yeah. But even before that, it is growing within bounds, right?
It's growing within bounds, yes, yes.
So
Yeah,
you
it grows
can
within.
peaks and things
Yes.
not exceed-
But by the way, that's closely parallel with what entropy does. It grows with fluctuations within bounds.
Where's the heat death of the universe? Where's the heat death of the universe?
No heat death.
No heat death.
Yeah. Now, if there's a finite number of particles, in the end, there's a ballet which will get ever more perfectly defined, but it's limit cycles, so that essentially, with a finite number of particles, after a while, nothing particularly new happens. Most of the systems will break up into Kepler pairs, which will go off and they will be ever better synchronized. And then there will be singletons and Kepler pairs. Now, we're beginning to explore what happens. Can we extend these ideas to infinitely many particles? Again, I'm doing this under influence from Poincaré. And there I really think there could be an infinitely creative universe that would go on forever increasing. As you allow ever more particles, there's ever more combinatorial possibilities. So,
But for finite dimensional, C cannot grow to infinity.
sorry, fine.
For finitely many particles, C
Oh, the complexity always goes to infinity.
it goes to infinity.
Oh yes, the complexity is bound to go
So
to
if
infinity.
you replace complexity, like if you replace entropy for complexity, that's your heat death,
Sorry?
right?
Well, I was going to ask another question. But
Okay, sorry.
no.
That what it seems to me is that the usual arrow of time is to say time flows in the direction in which entropy increases.
Yes, that's the standard story since at the latest Boltzmann, if not before.
But what I'm getting from your talk is that you're saying, no, the arrow of time follows the direction of which this C constant that you have defined, this shape complexity increases,
Yep,
right?
yes.
So then, like, to this question, where is the heat death of the universe? Is like, your heat death is like this amount of, like, singletons and Kepler
Where
pairs.
nothing particularly new happens. Yes, that would be the
Well,
case.
But that's impossible. Where's dynamic friction in this?
There is none.
There is none.
Why is there no dynamic friction?
Because Newtonian theory deals with point particles. It's a
They
very...
have different masses.
Hmm?
They have different masses. The largest mass should produce dynamic friction because as it moves through, those little ones will fall in its wake. and then
Well, I
slow
mean,
everything down,
until
and then-
one has got, I mean, they basically, I mean, by the way, I don't think you see this in the actual universe, which is,
dynamic friction. That's look at any cluster of galaxies. You'll see the central CD galaxies, the most massive ones, and then how did they get there? They got there by.
oh, by the way, it's actually what I should have said. Certainly in Newtonian theory, you can get large clusters of particles forming. Yeah. So they will, to some extent, they will at least virialize at the center. So you can, in some senses, associate a temperature with them, which will be different for two. And then they will collide. And then when those two collide, there will be a growth of entropy. Because
I don't see any clusters here, like a cluster of galaxies that we have in the real universe.
But by that theorem I told you, you can create any galaxies you like that at least approximate galaxies in appearance.
I don't see anything that looks like a cluster of galaxies in any of those pictures.
No. But we haven't done those calculations. But just look through the Hubble Space Telescope, and you see galaxies. And these very good approximations to them at the level of, I mean, let's go back to the atomistic theory. The atomistic theory was that all that we see is really indivisible atoms. Now, interestingly, they said they had shape and size, but they were indivisible. Now, what we're doing is actually having pure point particles, but still with pure point particles, a good pure points on a white piece of white paper, a good cartoonist can do an image of Donald Trump quite easily. So you can just as easily do things that look like spiral galaxies. And Newton's theory will generate them out of alpha. That's a mathematical theorem.
So the idea is that you can have central configuration such that when you let it evolve under Newton gravity,
Yeah.
instead of just Kepler pairs, you can have like large clusters of Kepler pairs that orbit each other, and like you can have something that resembles more.
You can go to any shape you want. That's this remarkable theorem. You can go from the most uniform shape, which is not absolutely uniform, to any shape you want.
Any shape you want.
Any shape you want.
The gravithermal catastrophe says, I think, right, that eventually you're going to get lots of pairs out in the pin, right?
So the Russian has this theory, and Donald Lyndon Bell has a nice paper on it, the gravitational catastrophe, or the heat, whatever it is.
It's gravithermal catastrophe.
The gravithermal catastrophe. And basically, but by the way, the Russian put that system in a box and had them, and so did Donald Lyndon Bell. I mean, I beg your pardon, totally unreal. And this is a Hawking box too, as far as I know. Come on, tell that one to the Marines, that there's a physical box out there that's stopping these things. They fly out to infinity, or they go on forever. They go flying out there. But what's left, I mean, the conjecture is what's left is a very tightly bound Kepler pair.
Right.
In many cases, that's what will be left.
But in the universe, the dynamic friction which produces clusters of galaxies does not depend on any box.
No, but I'm glad about that, and I'm saying Newton can approximate that, I suspect, rather well.
Well, then I don't see it anywhere. I don't see it.
Okay. If there were three really heavy masses,
Yeah.
they would
or
sink
just
to
one,
this-
or just one.
Well, let's
It gets bigger. Oh, they don't. Do they stick? to each
They
other?
don't stick.
They bounce off each other.
They pass past each other, arbitrarily close, right? That's why there's no pressure, right? So if you just have point particle, like if you put three heavy masses, they sink to the center, dump all the kinetic energy into lots of little guys.
But then any pair would get harder and harder and harder, and then it would be
Yeah.
essentially a bigger mass, and then it would run into another one, and then it would get
okay.
harder and harder, and
You
more
have
massive.
you have two hard pairs coming
Yeah,
together,
yeah,
right?
yeah.
You don't get a quartet that's hard.
No, you get a triple and one.
Yeah, okay. You get a triple, but the
Yeah,
triple
and
is
that-
unstable.
No, I don't think so. I think
You
I don't know.
get a triple and you get another guy in. You don't get a quartet. I think that's the.
By the way,
and
there
then it gets weird.
there is this
Right.
famous result, which is expressed with an absolute time, where with 5 particles you can get 4 particles. You can get all the particles going off to infinity in finite Newton time.
Oh, there's
That's CIA, CIA. But that's still a perfectly well-defined curve in shape space. There's no problem with it from the point of view of shape dynamics.
The problem is that you're ignoring friction.
Yeah. I mean that's.
Yeah, but with point particles there is no friction.
Well,
But there is effective
not
friction.
one.
I mean, I gave the example of 2 clusters that have more or less virialized, at least in their centers, and you can approximately give a ratio of temperatures with them. And then if they collide, then there will be sort of friction effects. Yes, that can happen, but Newton can do that.
Well, not here. That's not a result of friction.
No, but because of this result of that thing, that you can get those things that will form, and they could pass through each other.
I'm sure if you had friction, you'd get
I just want to go on to the very last thing, I think.
Okay, and
I just want to say, my conjecture is that you should replace the idea of laws of nature by a law of the universe, from which local laws of nature emerge through the evolution of the universe. And so, I mean, I would say that the law of the universe is that it's a constrained Hamiltonian system. And I already showed you that very significant book of Dirac Lectures on Quantum Mechanics, which is a much cited book by people working in gauge theory. And then the simplest examples are n-body Mach-in solutions with both those things 0, and then subsystems form with all possible values, provided the totals are 0. So the law of the universe is all solutions begin maximally uniform at alpha. For that I require the principle of sufficient reason to justify that. But then there are emergent laws of nature which are governed by the principle of least action and allow all possible conserved quantities. And this is true for arbitrary large n. And then I think, but this is still very tentative, that these ideas, at least to some extent, can it be extended to infinitely many particles. And I think the very last slide is this one. Is cosmological inflation necessary? So this is, I took the trouble to check up Harrison of the Harrison-Zeldovich fluctuations. So, I mean, the great thing was Harrison and Zeldovich proposed the exactly scale invariant fluctuations at some stage. Harrison says, well, let me read you what. Of the various, let's see what Harrison says. Of the various problems relating to galaxy formation, the most perplexing is the nature and origin of the initial conditions. The initial homogeneities which eventually develop into galaxies cannot arise spontaneously in an expanding universe, and must therefore already exist in primitive form when the universe begins to expand. It is proposed that the initial homogeneities are fluctuations at the threshold of classical cosmology. He's implying there that the quantum stage becomes classical. And so the current paradigm requires this exponential inflation-driven expansion and quantum fluctuations of the inflaton. And the start and end of inflation are increasingly seen as problematic now, although the fluctuations that are generated are terrifically successful. But about 10 years ago, I was at a workshop in Durham where Peebles was. So Peebles anticipated this famous thing which shows all where the powers are in the microwave background. Peebles essentially got that several years before inflation arrived on the scene, and he developed the idea of Joe Silk. I forget what Silk's work. So Silk was the first and Peebles the next. And that's essentially what Peebles got the Nobel Prize for a few years ago. And I asked Peebles, what would he say inflation had brought into the thing? And he thought quite a long time, and he said that the slope is not quite 1, but slightly less than 1. But that was only a gut feeling, I think, of the main Russian chap, I can't remember his name, who was pushing inflation early on. So I think that's quite interesting. So at least Newtonian Big Bangs give the desiderata qualitatively, because those fluctuations, the minimum thing, if I go back to the in that paper that I cited by Batty, Gibbons and Hawking, they describe that distribution as being glassy. And there's a nice paper by the Irishman Michael, anyway, it's an Irishman. And anyway, he says that normally things are represented in Fourier space as a straight line. But if you want to see what the inhomogeneities look like in real space, they look like a glassy liquid. And so that's not a bad approximation on the left to a glassy liquid.
I can guarantee you that the n for neither of those is anywhere close to 1.
Well, I mean, this is a conjecture, and if you can do that, then I'll be glad to.
Because I looked at so many maps.
Sorry?
Thousands of maps of the cosmic background, and we were doing power spectra, we were doing correlation functions, and this the one on the right, for example, have a giant peak at about that average separation that you're seeing. I don't know how many centimeters that is, but they're anti-correlated, and that produces a giant peak in the power spectrum at one point. That's not n equals 1. The power spectrum is not linear all the way, though. There's a turnover, isn't there? Well,
I mean, I'm not an expert in this. I'm just throwing it out as an extreme possibility, as a most optimistic possibility. But I mean, a lot of more work needs. I think that really brings it to the end. But thank you very much for all the questions and critique. At the least, I hope to have persuaded you that Newtonian theory is a great deal more interesting than people realize. Yeah.